Okay, so here we have a problem that deals with angular momentum, and this problem comes from the textbook Physics for Scientists and Engineers with Modern Physics by Serway and Jewett. This is from chapter 11, I believe. So let me just read the problem. So it says a conical pendulum consists of a bob of mass m in motion in a circular path in a horizontal plane as shown in the figure. During the motion, the supporting wire of length L maintains the constant angle theta with the vertical. Show that the magnitude of the angular momentum of the bob about the circle's center is this, right here. Okay, well, first thing I'm going to do is actually just redraw the triangle that is created, just a little bit bigger. So let me do that right here. Okay, so this triangle corresponds to this one right there, where this angle is theta, this is length L, and here is the mass m, and it's traveling around like this. We could say this is its velocity vector. Okay, well, I guess let me just label the legs of the triangle. So this side would be L sine theta, and this side would be L cosine theta. Okay, so, well, first of all, the definition of angular momentum is equal to r cross p. So it's the position vector crossed with the momentum vector. So in terms of the magnitude of this would just be r p. So the magnitude of r, the magnitude of p, times the sine of theta. This is just the definition of the magnitude of a cross product, where p is just the momentum. So we could say rmv sine theta. And I should note that this r right here is the position vector from the origin, and the problem says about the circle's center, which means that they want us to consider this point the origin, which means that, I'll draw it in blue, the position vector would be from the origin here straight to the particle. So if you can kind of see, I guess I'll just draw a quick top-down view. This would be like if we're looking above. So the mass would be here, it'd be traveling with a speed v. Here's the origin, the position vector would go here, and this is all to say that this angle between them is 90 degrees. So that angle is this angle right here. So rewriting one more time, we'd say RMV sine of 90, which is just 1. So we can say that L, so the magnitude of L, magnitude of the angular momentum, is just RMV. Okay, so now R, which is this blue vector that I drew, well, that's just the radius of the circle. And from this triangle right here, we see that the radius of the circle is actually just L sine theta. So we can say that this is equal to L sine theta times mv. Okay, so we're getting there. So the next step is to actually, so right here I drew a top-down view. So I'm actually going to draw a sort of a side view over here. So here's the mass, right? And it's traveling in a circle that is into the screen. So we say from this perspective, this would be the force of gravity acting. And then there is tension in this rope right here. So like right here, there's some tension pulling up at an angle. So from a side view, we'd say, here's the tension. And then let's see, draw some dotted lines. I'll make them straight. Okay, so if this angle with the vertical right here is theta, and that's just from this picture, that means that this angle is theta because they're alternate interior angles. So we are now going to apply Newton's second law. So we say that F net in the x direction, I guess I should label my x and y. Well, this is going to be y, but in this case, I'm actually going to call this direction positive x because the object is actually accelerating in this direction because it is moving in a circle. So the tension in the rope actually provides a centripetal acceleration. So I'm going to call this direction positive, because the object is actually accelerating towards the center of the circle. So I'm going to say that the net force in the x direction is equal to mass times centripetal acceleration, and the only force in the x direction is this guy right here, which is the component of the tension. I guess I should call this just T for tension. So this component right here is actually going to be, so if we imagine moving this blue vector just up to here, it would be T sine theta. So that's the only force in the x direction. So we're going to say T sine theta is equal to mass times centripetal acceleration, which is just v squared divided by r. Okay, well, this r down here, this is just the radius of the circle, which again, like up here, is just L sine theta. So I'm going to substitute that in. So T sine theta equals mv squared divided by, oops, not r, L sine theta. Okay, so we're trying to get L equal to this thing right here, which has no V's and no T's, which we have a T right here, V here, and V here. So we're going to need to get rid of those variables somehow. Well, first thing I'm going to do is I'm actually going to, I'm going to solve for V squared right here. So that's going to be, mv squared times, mv squared equals T L sine squared theta, and then v squared equals TL sine squared theta over m. So now I have an expression for v squared. So instead of taking the square root and then substituting that into here, I'm actually just going to square everything. So I'm going to square this, and I'm going to square this, which will give me v squared. So I can substitute in. So, so L squared, big L squared, capital L squared, equals little l squared times m squared times v squared times sine squared theta. Okay, so now I can actually substitute this directly in for v squared here. So I'm going to get L squared is equal to So I'm going to put the v squared out front. So I'm just going to copy this. So this is v squared. So L squared equals v squared times little l squared m squared sine squared theta. Well, this m will cancel with that m. So simplifying, we have that L squared is equal to T L cubed sine to the fourth theta. Okay. Am I missing anything? Nope. Okay. Well, if we go back up here, it says show that L is equal to this. Well, we're close, but there's no T's in there. And we have a T right here. So we need to get rid of that somehow. Well, if we go over here, back to this side view, we're going to now apply Newton's second law in the y direction. So we say that F net in the y direction equals, well, it equals 0 because the object is only traveling in a horizontal plane, so it's not actually accelerating in the vertical direction, in the y direction. So we can say that its acceleration is equal to 0, which means the net force has to be equal to 0. Well, there is gravity pulling in the negative y direction from right here, but then there is also a component of this tension right here. And I'll just draw that vector real quick. So that component is actually going to be t cosine theta. So we can say that t cosine theta minus mg, because the mg is in the negative y direction, equals 0, which just reduces to t cosine theta equals mg. Well, now we have a way to substitute, or we can solve this for t, substitute that in here, and then no more t's will be left. So I can say that t equals mg cosine theta. Okay, so now over here, L squared equals t, but t actually equals mg cosine theta. So L squared equals mg cosine theta times L cubed sine to the fourth theta. Oops, I am actually missing. So right here, I canceled this m with one of these m's, but I actually forgot to add this m. So I'm just going to add that here. That m should have been right there, which means it should be here. Okay, so now L squared is equal to m squared g, m squared g, L cubed sine to the fourth theta all over cosine theta. And now the last step is to just take the square root. So I'm just going to say that L equals m squared g little l cubed sine to the fourth theta divided by cosine of theta all to the 1/2 power. And there we have it. This expression right there matches what they wanted us to show from right here.